Hi, welcome to the MPI workshop presented by the NSS XSEDE program. This was originally a two-day event with hands-on exercises that you can view at your own pace.
We're now prepared to attack something that's a much more substantial and much more interesting problem, and will take a good bit more effort, but we'll reward you in that if you do this exercise, you are an MPI programmer. So, as I'll note several times here, some of you will be able to do this exercise in the exercise time we have in the workshop itself. Some of you may work over, tonight, depending on what time zone you're in. We might be wrapping up early today. You'll have time there. You might, depending on what time zone you're in, you might have time tomorrow morning. Some of you may put a lot of hours in and get this done. Some of you may do it in just an hour and a half or something. Some of you may have to fight with this a little bit longer, depending on how rusty your skills are. I encourage you to do that. We won't spoil this problem tomorrow in our review session for this. You can continue to work on it. I'm just going to review some of the aspects of this problem. I'm not going to force the solution in your face, although there's a solution sitting out there in the exercise folder already, a solution that I've written. I'm not going to stick it in your face, so tomorrow you will have the ability to continue to work on this problem. I encourage you to do whatever it takes to complete this problem, because if you do, you're an MPI programmer. And that is, I mean that sincerely. You understand how MPI works. You're not an expert, you're not experienced, but you understand how MPI works. So, with that in mind, let's jump into what this problem is. It's a Laplace solver. This turns out to be a fairly important class of numerical problems that we're going to apply to a very intuitive, simple to understand application. Our application is going to be a square metal plate that's at 0 degrees. And we're going to heat this metal plate in some slightly irregular pattern around the edges so that we end up with some final temperature distribution across the plate, some final steady state. We're going to heat this plate at 100 degrees down here in this corner with these heating elements that taper off to go from 100 degrees to 0 degrees. And we're going to keep these two edges here at 0 degrees. So we kind of got this heating pattern that would suggest that our final temperature distribution might look something like this here. We've got a gradient, very hot down in this corner, very cold out in this corner. And we're going to numerically solve this exactly and see if we get something that looks like this. That's our physical problem. This is a good problem because not only is it intuitive, but it's the exact same problem that I use, starting with the same serial code, in my OpenMP and my OpenACC course. So you know I'm not rigging something here to show you how easy MPI is, and then you're going to go and try to apply this to your own problems and find out that it's not. This is really representative of a wide class of problems. And the way we're going to approach this problem, the attack that we use here, is representative of an attack used on an even wider class of problems. The domain decomposition that we're going to use here applies to a tremendous number of MPI solvable, parallelizable problems. So that's the reason we picked the problem. From the mathematical perspective, we're solving a Laplace equation. If your methods, your mathematical physics are a little rusty, this is nothing more than the equation that governs any kind of phenomena where a point in a field is really equal to the average of the surrounding field. And that applies to many, many problems in electrostatics, and fluid flow, and here in temperature. So we're basically saying that this differential equation here, which we won't have to worry about explicitly as a differential equation. This differential equation here is telling us that any point on a metal plate is equal to the average of its neighbors. And if you think about it, that makes sense. If we had a hot rock and a cold rock and we stuck a rock in between it, the temperature we'd expect it to come to would be a lukewarm rock, right? So that's all that this equation says. And for a metal plate, that's equally true. Nice thing about it, it turns into a numerical method that's also pretty intuitive. Our numerical method to solve the Laplace equation on a square grid, which is how we're going to represent our metal plate, is simply to say that each point is the average of its four neighbors, and we're going to keep iterating that over and over on the grid until that becomes true, until it quits changing from one iteration to the next. In other words, we're going to say that this point A here is equal to adding together our four neighbors to north, east, south, and west, or up, down, left, right, however you want to think of it, and then dividing by 4. That's just the average of our four neighbors. We're going to do that. We're going to keep going over the grid and doing this. We'll find that it converges on a solution, and eventually it ceases to change, really. It changes very little from one step to the next. Our definition of very little in our code will be whenever no point on our entire grid changes more than 1/100 of a degree from one iteration to the next, then we've converged on our solution. So the science of our code is really all compacted here in this loop right here, in the Fortran C versions of our kernel of our code. That's sometimes how you refer to these kind of things. The kernel of our code is just a couple of loops over the X and Y, or the I and J directions here, that keep iterating to find out our new temperature versus our last iteration over this grid. We really want to have two arrays here, our current solution we're looking for and our old one. If we try to have one temperature grid and find points on it, some of the points will be ones that we updated if we're rasterizing over the grid. Some points would be new ones, and then some points would be from the last time step, and it would be very confusing and improper. And so instead we have the temperature and temperature last, where last is the last time step, and then we use that to find a new temperature. And when we're done, we take our new temperature, copy the temperature last, and keep doing that over and over until there's very little difference between the two. To put this into the main loop of the code, the kernel of the code that's really going to do all the logic here, is very straightforward. This is the C version we'll look at first here. It's basically saying we're going to have a while loop that says keep doing this until our maximum temperature change, dt, which we'll look for down below, till our maximum temperature change is smaller than some value. And this will be, as I said, 100th of a degree is the one that we're going to use. So while the change in temperature on any point is greater than 100th of a degree, keep going. Or the user can also set in some patience limit here, some maximum iteration count. The user can say, run this for 1,000 iterations and then stop. I don't care where the solution is. So until we exceed the maximum iteration count or until we find the solution, keep going. That's what this outside loop is. Inside that loop, we do our calculation that we just looked at, our Laplace solver here. Jacobi iteration is what this is called. So we do our Jacobi iteration inside here, and then we want to copy the new temperature array into the old temperature array here. While we're doing that, that's a good time to look for the maximum temperature change too. While we're copying over each element, we'll see what the biggest change between any two elements is, between temperature and temperature last, and we'll capture that to know if it's time to quit or not. And every 100 iterations or so, we'll track our progress. We'll print some data out. In our case, we'll just print out that five little elements from the bottom corner is what the print routine does, because that's probably where most of the action's happening. We can see what's going on there. We don't want to dump the whole grid out to a million points every time. There are a couple subroutines that were invoked there. The one I just said, print progress here, track progress, it's just going to print 5 elements out every time it gets called, which is every 100 time steps. And then we have our initialization routine, which sets the temperature of the grid equal to 0, the metal plate, and also sets our boundary conditions, our heating elements on the edges, which we won't change, so this is what they get set with. So it's very straightforward. Here's the entire code. Don't squint at this tiny text. I just put this up here so you can see. Here's the whole code. Here's the kernel that we just looked at with the guts of the logic. So this is the whole thing. It's not overwhelming, so take a look through it. You should be able to pretty much understand it. We'll step through the Fortran code, which is exactly the same logic. We'll reiterate everything I just did, basically. We've got a loop on the outside that says, while our temperature change is above some threshold, keep going, and unless we've exceeded the maximum iteration count that the user allows us. Inside of there, do the science part here, which is to do this Jacobi iteration, find the average of our neighbors, and keep updating our point with that. Every time step, update our temporary last array, and every 100 time steps, print some results out. So it's the exact same logic, same kind of subroutines. Here's the initialize subroutine that sets the grid equal to 0 and then sets the boundary conditions on the edges. And here's a print subroutine that dumps out some values every 100 time steps. Here's the entire code. So it's no big deal to understand. It's not an overwhelming amount of code. So here we are with our starting point. This is our serial code. And again, look at this. Make sure you understand the serial code and what it's doing before you attempt to try to do anything. But what we will do is we're going to take the classic, almost universal approach to parallelizing a code with MPI to make a really, truly scalable code. And the first thing we're going to do is what's called the domain decomposition, or in other words, how do we split up our data structures? This is the way you parallelize codes, again, with MPI in the vast majority of cases. We need to break up our data into a bunch of pieces. And as much as you might think this is a routine thing to do, because it's the first step in MPI, so clearly there's some simple patterns in how to do this. This is where people tend to go awry the most, and it's the most important step. If you do a good domain decomposition, the MPI code almost writes itself. It becomes very clear what messages have to go where, how you've broken up the data, and how it has to communicate. If you do this improperly, then you got a disaster in the making, and usually by the time people figure this out, that they're really committed to it, they put a lot of effort in. They're sunk in. They're at the end of of a dead end, it's very hard to salvage a lot of that effort. So you really want to put some effort in here in the domain decomposition. Sometimes it's intuitively obvious you're in the right track. Other times, for some problems, n-body problems, things with very regular shapes, it can be more difficult. You're lucky in that you're not pioneers in this. MPI has been around a long, long time, as we've discussed, and consequently, a lot of these techniques have been well developed, and there's a lot of literature out there with a problem that probably looks a lot like yours. Also, there are a lot of people that do this kind of stuff, or, well, not enough people that do this kind of stuff, but there are people out there that are experts in this, and you can seek their advice on this domain decomposition step, and then if that's firm footing, your progress from there on out will, like I said, most likely be self-guiding in some respects. We'll see that with our Laplace code here. Okay, so our domain decomposition in our case is we've got a square metal plate. Let's break it up into pieces. One thing that people do more often than I can understand is to say, okay, I'm going to take and give each one of the processors, let's say we've got 4 here, a copy of the entire temperature array, the whole metal plate, and then they'll operate on some small piece of that plate or something like that. This is bad for a variety of reasons, and the number one reason, well, one of the reasons certainly, is that any time you're doing a domain decomposition and you find yourself with a global data structure, with a data structure that all of the PEs have a copy of, you should be very concerned right away. That's a sign that something probably not right is happening. This is not for trivial. You might have a trivial small data structure that's got some information or some data or something, that's fine. But whenever your main data structure, whenever things that are megabytes in size are being copied, so that all the PEs have copies of that, it's a bad sign. One of the things you're doing is you're starting to write a code that's not scalable in the memory sense. One of the ideas of writing an MPI code is that we take our weather map and we break it up into 50 states, and one of the wonderful things is each one of those processors now has much less space, geography in our weather map that it has to worry about. It's got 1/50th of the area on average, and so it needs a lot less memory. You might look at that as it's got a lot less memory and now can fit into memory. You might look at that as it's got a lot less memory. Now I can expand the grid and get better resolution and better results because I can use all of that spare memory to have a finer grid. But however you look at it, you should not look at it as I got a copy of the map of the entire United States in each one of these processors, because that doesn't buy you any memory scalability. You're not able to do anything now. You're still trying to cram the whole thing in each processor. So no global data structures. It's just a bad idea if you find yourself heading down that path with this problem, with any other one. What you do want to have is a data structure that just shrank proportionally to the number of processors. In our case, we're going to focus on 4 processors here. The ideal case, again, would be very flexible and run on any number of processors, but we'll think about 4 processors to keep us all kind of on the same page. So with 4 processors, we might hope to break the plate up into 4 squares just like this. And that would be pretty good thinking. That's pretty sound thinking. Each processor just has 1/4 of the plate, takes up 1/4 as much memory, which would mean we could also, again, take the opportunity to make the problem much finer. If we've got a 1,000 by 1,000 plate, maybe we knew to get really correct answers, we'd like to have a plate that's 10,000 by 10,000. Well, once we start breaking it up into small pieces, we can do that. We can fit a finer, global grid, spread it out over a lot of the memory available on all these other PEs. So we're on the right path here. We're breaking this metal plate up into 4 pieces. This is great. This is not too bad at all. And you could approach the problem this way. I'm going to suggest something that's similar, but going to be even a little bit easier for us as very, very beginner MPI programmers, and that's we're going to break it up into strips right here. That will save us from the slight complication of having to send messages in 2 directions here. Now tomorrow in our advanced MPI stuff, we'll see how easy this is to do, to send data in 2 directions or in higher dimensions, in many directions, and do all kinds of fun stuff. But to keep life simple right now, I will suggest that you might want to work with strips like this. That way messages, if we break it up into strips, only have to go in 1 direction, work in 1 dimension here, really. So that way we're only sending to our neighbors up and down, not left, up and down, and left and right. It's a simplification that is a little bit nicer. Also, it has the virtue of what if we want to break this up into, say, 5 strips instead of 4. Strips are a little bit easier than this. What if we want to break this up into 5 PEs? A little bit more complicated, right? So nothing wrong with this, but this is the way we're going to go. I'm going to suggest we're going to go here to start this problem. So if we break our plate up into 4 strips like this, we're off to a good start. Now we've recognized the fact that the global 1,000 by 1,000 grid now no longer exists anywhere except in our heads. It is now an abstraction. Nowhere in our code is there any more 1,000 by 1,000 data structure. That's a good thing. Our data structures now, we've got arrays that are 1,000 by 250 roughly. That's our new data structure. Nowhere is the 1,000 by 1,000 grid really still around. It's just, like I say, it's on our graph paper. It's there, but it's not in memory anymore. Each PE has one rectangular strip of 250 by 1,000. Okay, so they each have these strips. They could run away mostly and do most of the science of solving this Jacobi iteration inside the strip. The only place they really need to interact with their neighbors is along the boundary. And this is typical of a lot of data decompositions. You break your problem up into pieces, and the physics only bleeds across the boundaries. There's a lot of locality and a lot of different types of physics, and it comes down to data decompositions can take advantage of that. You can break things up into pieces. Our weather map we break up into pieces and say the weather only happens between states on their borders. Now, that's not always true. We could be drawing, say, a gravitational model of the solar system, and it's an n-body problem. And every particle interacts with every other particle, and it's harder to draw boundaries and things like that. There are classes of problems like that. But there's a huge class of problems where the physics is local, and we only have to worry about things on the boundary. And for these problems, this technique is very common, where we break the plate up into pieces, and then we end up with halos or ghost cells, zones on the border that we use to take care of this communication along the border, where we do need to know about our neighbors. So these halo approaches or ghost cells are used for a lot of problems like this to fit into stencil patterns. So you're going to see this a whole lot, and it works well also with very, very irregular problems. So this could work well with a problem, say we're trying to do finite element analysis on the Golden Gate Bridge, and it's got a very weird shape. When we break it up into pieces, it's got weird boundaries and everything. This works just great with weird boundaries too. But it only works where our physics is only going to be, we only need to communicate between nearest neighbors on an edge, on a border. But again, that's a huge class of problems. So in this case here, we've broken our metal plate up into 4 strips. Now we want to communicate on the borders. So we have to pay a little bit of attention, and this is where maybe most of your attention in solving this problem is going to go, is paying attention to the indices here. You know, hey, welcome to programming. You got to pay attention to the indices. So the indices here, and the way we're going to break this up, amount to the fact that PE0 has, on this connecting border here, is going to have a row 250 that is really the edge of its plate, the last row in its plate that it's responsible for. But we're going to add in a row 251 here that's going to contain the data from the last real row of PE1. So we're going to keep a copy of row 1 from PE1 here in row 251. Notice that it's not row 0 of PE1. Row 0 of PE1 is its ghost zone, which corresponds to row 250 of PE0. So there's a little bit of overlap here if we were to shove these pieces back together. So we want to have the ghost zones on each one of these PEs containing the data for its neighbor. It's not responsible, the PE is not responsible for calculating the value in the ghost zone. It gets those from the neighbor, gets a copy from the neighbor, but it uses that data when it's calculating its own row along the edge. So PE1 here, for example, needs what's in this red ghost zone to calculate its values along row 1, but it never updates row 0 at all. Instead, it gets the copy for row 0 from PE0. From PE0's row 250. And meanwhile, PE0 is doing the same thing with row 251. It's grabbing row 1 out of PE1. So that's the ghost zone geometry here. And you pay attention to it, and it makes perfect sense, and it works out very well, but just make sure you understand this structure. And it works the same across all the PEs here. So this is what we're going to do. However, we're now sending for the first time, in any of our examples, multiple elements. I mentioned to you earlier, most problems involve sending not one integer or one floating point number, but sending arrays and subsections of arrays, actually probably more than anything. So we need to send a subsection of array here. So for the first time, we're going to send multiple elements. And so now we're going to use that count parameter in our sends and receives that we haven't been using before. So we're going to use that count parameter, and unfortunately, it's the C and Fortran layouts in memory of arrays are exactly opposite enough, different enough, that in C, when you send a strip of memory, you're sending across the row. In Fortran, when you send a strip of memory, you're sending down the column. So it's going to make our Fortran and C solutions a little bit different from each other, rotated to each other. So a little minor bit of confusion. Don't worry about it unless you're a person that spans the Fortran and C worlds, which is not that uncommon. A lot of times in numerical methods, you do need to use a Fortran library or vice versa, in which case you're aware of this problem, or you will become aware of this problem. So rows in Fortran are columns in Cs and vice versa. But we're going to send contiguous strips. So if we want to send a contiguous strip of an array in C, we point it at the first element that we want to send. So in C here, if we have this array 8, 12, so it's 8 by 12, we would point it at, in this case here, we would point it at 3, 1. And 3, 1 is going to be counting from 0, 0, 1, 2, 3, and 1 is going to be 0, 1 here. And if we send 4 elements, it means we're sending this chunk of this array right here. So that's what we'd send. So we can send strips of array in C as long as they're contiguous like this. Now tomorrow with advanced MPI, we will find out that MPI is wonderful at sending not just a contiguous strip out of an array. We can send blocks from arrays and rows, and we can send diagonals from arrays and sub-blocks. We can define anything we want. We can be in 3 dimensions. We can send a sub-block of an array with no problem whatsoever. So MPI is very capable of dealing with user-defined, user-definable data sets, subsets of arrays or anything else. No problem. But today, again, for the sake of keeping our beginning problem simple, we're going to just send strips that are contiguous in memory. And that's fine, because that's all we need to implement our solution. Now in Fortran, we'll see when we look at the solution, it's the same thing, only we're going to rotate the whole problem, because in Fortran, if you were to send 4 contiguous elements in an array, it would correspond to this. So that's just life with Fortran and C. I will point out, though, because it's impossible for me not to note this, it's such an important performance consideration, I will point out that you should always, for serial performance reasons, this is not an MPI issue, I'm just going to digress for 30 seconds here and point out that you should always make sure that in your codes, the innermost loop in C corresponds to the last index. In other words, if we've got a nested loop here over I and J, the innermost loop, J, had best be the second index. That's what makes sure that you're going through memory in order and you're not jumping all over the place, because if you jump in C, if you go this way, you're going through memory in big jumps, big strides through memory. It's a raster pattern. So in C, you always want to make sure that that last index is the one on the innermost loop. Fortran, again, is the exact opposite convention. In Fortran, you always want to make sure that that innermost loop is the first index, and you work to the right from there. So C and Fortran are exactly backwards, but you definitely want to pay attention. This is a serial computing issue. It's nothing to do with MPI, but it has a huge performance implication. If you don't believe me, try and flip them here and see what it does to performance. And in your own codes, if you've just ignored this and just taken your best guess, go back and look at those loops. If you order them correctly, you can get huge performance improvements just because things are next to each other in memory. And modern computers are much faster accessing cache lines in big chunks at a time in the right order. It's a topic I'd dearly love to go into. We don't have the time to, but this is the first order correction you should pay attention to. So in our case, we're good though. We can send multiple elements in the array at once in our messages. So we can do things like this now. In C, we can say, if my p is not equal to 0, then up equals my p minus 1. So we can send this whole row here. We point it to the first element that we want to send in the strip we want to send. We point it to that first element and say send columns number of elements. And it'll send this entire strip going across this column, and we can send it up. So this is a way to send it. MPI also has some clever little things built in to make your coding a little clearer, like MPI proc null, for example. MPI proc null means it's basically a black hole you can feel free to send messages to, and it won't cause problems. And so we could write a little bit of logic like this if we wanted to. We could say up equals my p minus 1. If my p equals 0, then up equals proc null, and then we can just do a send, have all of them send. Meanwhile, p 0 will send a message, a bogus message to nowhere, and it will cost nothing. So MPI has a lot of flexibility and ways to implement things. Tomorrow in Advanced MPI, we'll see a lot more evidence of that. It's just got a lot of things to make your code and your algorithms clean and sharp. Fortran is the exact same process here. I'm going to step through it again quickly to show you, except that now we're dealing with sending columns instead of sending rows. We're breaking our metal plate up into 4 pieces. We're dealing with the same ghost zones like this, the same ghost cells, except they're columns now. So once again, you want to send this row here to this ghost cell. You want to send this row here to these ghost cells, and it all works out. So the logic would look something like this. This is the same as the logic for the C code here. So this is the basic idea of implementing the communications part of the code, which in most MPI codes is a pretty distinct section of your code. You've got the compute phase, and then you've got this communicate phase. Most codes, like I say, this is pretty distinct. You might have several iterations of this, but in general, a lot of codes just simply have compute phase, communicate phase. This has implications I mentioned earlier for the networks and everything else, because all the communications are trying to happen at the same time, so you best make sure your network's up to snuff if you want to have good performance. But that's not MPI's problem. That's the hardware person's problem, the configuration builder's problem. So in our code here, we've got the science, which looks a whole lot like the serial code. When we're done here, you're going to look back and go, wow, it's remarkable how little I had to change the science of the code, but we had to add in this communicate phase. You'll also find, and this is a valuable lesson too about MPI, we're going to have to go off into those subroutines and see what's going on there as well. One of the drawbacks to MPI is that anywhere that data structure that you're decomposing lives, you have to go and track it down and make corrections for it. This is a little bit different from some of the simpler ways of doing parallel coding like OpenMP, for example, where you might work a loop at a time or a subroutine at a time. You don't have that luxury in MPI. The price you pay to end up with this fantastic scalability is that any data structure you decompose, you have to find anywhere it is in the code. And it doesn't matter that it's a subroutine, that the person that wrote it graduated 5 years ago, and you can't get in touch with her to save your life, and it's, you know, it's just very dusty code. Well, you know what? You got to go figure it out, because anywhere the data structure lives, you got to track it down. That's MPI. In our case here, we've got the data structure living in our boundary conditions and our initialization code. So you're going to have to go and look into that code and figure out how to break it up. The old serial version set these boundary conditions like this, temperature starting at 100 down in this corner. You're now going to have to go and break it up into, well, the appropriate pieces. I think this is suggestive of what you want to do with your logic. I've given you 2 ways to do this exercise. You can start from the serial code from scratch, nothing in there, it's just a straight up serial solution. I've also got a template code that has some hints in it. I'll show you some examples of what that looks like in a moment. And this gives you some idea where you might want to stick stuff in. So they're all sitting there right now. You've got the serial code in C and Fortran, the template code. There's also solution code in the solutions, which I urge you to give a good faith effort and not look at the solution. The template codes look like this. They've got these very non-compilable braces in them. They're not color-coded, of course, in the code, but there are these or greater than signs in them. So you've got a bunch of greater than signs with some suggestive comments of what you might want to stick in there. So, for example, the usual MPI startup routines, right? I'm not giving away too much if I say you might want to stick in, MPI init in here, right? So this kind of is a clue as to what you want to stick in where. It's the same with the Fortran one. So you might want to use that for guidance. Or you might want to just look at this and use the serial code, work on the serial code, but take a look here as to what the hints are. There are a couple of common ways that you could go wrong here. They're mostly just not paying attention to the details that could happen in any kind of coding. You want to make sure that between temperature and temperature last, you get the boundary conditions right, that you get the ghost zone conditions right. It's just a matter of which indices go where. You want to make sure that you do the right job of copying and calculating from using temperature or temperature last where it's appropriate and sending and receiving to the right places. So it's very straightforward. These are not subtle things, but they're easy to get an index off. There are different reasonable solutions you might come up with, and you could deal with this in different ways. Now, you might think that the solution, right now, the serial version of the code converges. It comes down to the correct answer at 3,372 time steps. So if you typed in 4,000 for number of time steps, you'll find out that it stops here at 3,372 with the correct answer. So you might think that if the parallel version of your code converges at the same number of time steps, it must be working correctly. And that's actually not an unreasonable assumption. Matter of fact, it's an assumption that I made when I first did this. Turns out that isn't quite enough in this particular case because of the nature of this particular problem we're solving. You got to look a little bit deeper. For solving this particular problem, here's a working MPI solution. I graphed out the bottom corner and the temperature gradient across it. Actually, I just pulled this up from the debugger. I'll show you the debugger tomorrow. You can do this kind of stuff as the code's running. It's pretty nifty. So here's what it looks like as it's running when it finds a solution. And there's a gradient in the bottom corner of the temperature going down to 0. And that looks kind of like what I'd expect. Here's a version that's really broken. Matter of fact, it's so broken I turned off the MPI routines. And so here's the line between PE3 and PE2 on the bottom. And I just turned off all of the MPI right here. So nothing's right. It's making a mess of it. They're both solving the code in their own little worlds without trying to match along the border at all. And this is what you'd end up with, a broken solution. But it so happens that they still converge to 1/100th of a degree at 3,372 time steps. And that's because the place where it's last that converges is a very hot corner down here that's all here on PE3. So that means that even though, again, it seems oddly, it just seems unbelievable that the thing can converge in the same number of time steps even if it's a mess. That so happens to be the case here. So here's a quick way you can check for yourself. You can look at pick a data point. I picked one that's along that corner here. I picked a data point right here, and I just look at that and say, is it the right value? Does it correspond to what we get in the serial code? That's one easy way to do it. I mean, you could dump the whole thing out and look at it. It's a million entries. It's not that hard. You can visualize it yourself pretty easily. I dumped it into Excel real quick just to make sure. The debugger I'll show you tomorrow makes this kind of thing very, very easy. But we don't have the debugger yet. I don't want to confuse you with tools and whatnot just yet. So you might just want to look at a magic point. And if you want to, I've given you a magic point right here. 0.75900 happens to be right here on this edge on the border. So if that point's about 1 degree, you're probably good. If it's not 1 degree, you might be off. So there's a quick reality check if you'd like to see what's up. As I said before when we started this exercise is definitely doable just on the hands-on time that we've got allocated today and tomorrow. And many people do it in that time. That used to historically just be, I kind of assumed people would. But then I kind of realized that there's no reason to rush this. It is an important problem for you to do. If you do this problem and you get it working, you understand MPI. I mean that sincerely as somebody that's loath to unleash unprepared, ill-prepared, and overconfident programmers on the world. If you can do this problem, you're competent to start using MPI. So do this problem. Means I won't spoil it tomorrow with our review. So if things aren't coming together quickly for you and you're struggling with it, I'm not going to come in tomorrow and spoil the whole thing and you won't get a chance. You can take all the time you need. You've got your accounts for a couple of weeks after this workshop. You can take that time to complete it if you'd like. You will be able to. But please give it a good effort. So some of you, like I said, depending on your time zone, might have time this afternoon or tomorrow morning. We have exercise time in the workshop, plenty of it tomorrow. I'm happy to provide as much help as necessary during that exercise time. So go ahead and get to work. The copies of it are in your exercises folder that you've copied over. There's the starting serial code or template codes, whichever you prefer in Fortran or C. The hint ones are there. Again, have the browser window open next to you while you're doing this stuff, so you're not trying to remember what all the parameters are. It should compile the same as the codes we've done so far. It should run on 4 PEs. So go ahead and get to work.